Good evening, class. Well, it's evening for me when I'm making these notes. Welcome back to IB Mathematics. Our last lesson, Unit 14.1, was about tangent lines to curves. And Unit 14.2 is very, very related to Unit 14.1. Instead of tangent lines, we're talking about normal lines. So in our previous lesson, we talked about tangents, which you can see in this picture. They're lines that touch a curve at a given point without going through the curve at that point. And these are the same exact examples that I gave you in the notes that we did yesterday. Well, for me, it was yesterday. And we have a point of tangency here. We have a point of tangency here. See, at that point of tangency, the line that I've drawn there has the exact same slope as the curve. Well, a normal line is perpendicular to a curve at the point of tangency. So this is a good example. So right here I have I believe this is y equals ln of x. So I just got an ln of x function here. At this point, with an unknown x value, so we're saying that x value is the value a and the y value is f of a, whatever you get when you plug this a in, I found the derivative and then did point slope form to give me this tangent line. And then the normal line is perpendicular to the tangent at the exact same point. So if you remember all the way back to Algebra 1, if you're trying to find a line that is perpendicular to the line you have, all you have to do is take your slope and flip the sign, flip the fraction. And now you have a perpendicular slope. So if my tangent line here had a slope of 2, this normal line would have a slope of -1/2. If my tangent line had a slope of, 3/4, then this would be -4/3. I think you can see where this is going. So then it's explained what was going on in this picture. So if point A is at the point of intersection of a tangent and a curve, meaning the point of tangency, then the coordinates of the intersection is a comma f of a, which is labeled in the picture here, and the gradient slope of the tangent line is f prime of a, just like it was in the last lesson. The gradient of the normal then is -1 over f prime of a. Flip the sign, flip the fraction. So when you use your point slope form, you get the exact same thing that we had in the last notes, but instead of, major typo, missing my negative sign. Sorry about that, folks. There we go. Anyway, instead of having f prime of a here, I have -1 over f prime of a. Flip the sign, flip the fraction, and there should have been a big minus sign in front of this one as well. There we go. Sorry about that. Okay. Jump right into the examples. Oh, before I get to it, you can see your homework over here? Yeah. These 3 questions that I've circled, those are the IB level questions. As far as I'm concerned, they're the only real homework questions. The other ones are Mickey Mouse Club, all right? These 3 are the kind of thing that I expect my students to be able to do. Please, don't insult my intelligence just by writing the answers out of the back of the book. I can't do those questions without showing work. There's absolutely no way you can. So what am I supposed to do, Mr. M? Well, I have a band of faithful followers that gets on Zoom with me every week and asks me for help on the homework, and I'm more than happy to help on any homework question. And by golly, they're the only ones that ever show up, even though I send out the code weekly. What I expect is a lot more than my 3 or 4 faithful followers in that Zoom meeting that I let you know about, because that is where you can get help on those 3 questions. Okay? Okay. So let's find the equation of the normal to this curve, 8 over root x, at x equals 4. Well, just like we do with tangents, I can't find a normal line without an x comma y. I have an x, I need a y. So I find my y value by simply plugging my x in. Y equals 8 divided by the square root of 4, which is 8 over 2, which gives me the y value of 4. So my x1, y1 happens to be 4 comma 4. Interesting, same point. 100% coincidence though. All right, now we need our slope. And our slope comes from the derivative. Well, in order to make the derivative easier to find, instead of writing it as 8 over square root of x, I'm going to write it as 8 times x raised to the -1/2. This way I can just use my simple power rule. Y prime, which is how we're going to find our slope. We're going to bring the -1/2 down to the front. I'll show the work. We're going to multiply it back to that 8. And then we're going to subtract 1 from this -1/2. It's going to give me -3/2. It cleans up to negative, and 1/2 of 8 is 4, over, because it has a negative exponent, square root of, because it's a 1/2 power, so to speak, x to the third. There. So again, it's on the bottom of the fraction because the exponent was negative. This square root bar is this denominator of the fraction exponent, and the 3 right here is this 3 right there. Oops, y prime. So now that we have our gradient function, we can plug in x equals 4 to figure out what our slope is. Okay. Ooh, that's off the screen. M equals negative 4 over the square root of 4 cubed. Well, 4 cubed is 64. And the square root of 64 is 8. And there you have it. The slope of this curve at this point is negative 1/2. But this says normal. You see, this is the slope of the tangent line. So our perpendicular slope, that's the symbol for perpendicular from geometry, would be flip this sign to positive, flip this fraction to 2. So slope is just 2. Point slope form. Y minus the known y value equals the slope at the point of x equals 4. There you have it. That is the equation of the tangent line. Ta-da! Shouldn't be that bad. Same exact directions, new curve, new x value. Find the equation of the normal to y equals e raised to the x minus 2 when x equals 3. Okay, first things first, we have an x, we need a y. So y equals, plugging in 3 is going to give me e to the 3 minus 2, which is e to the first, which is just e. How about that? Our coordinates are 3 comma e. Remember, e is a number. It's not pretty, but it is a number. Now we need our slope. Y prime. Okay, I'm trying to find the derivative of an exponential. Remember, the derivative of every exponential is write the original exponential and then multiply by the derivative of its slope. Whoa, derivative of its exponent. Sorry about that. Well, its exponent is linear, so the derivative of this exponent would just be the one that sits in front of the x. By golly, the derivative of y equals e raised to the x minus 2 is e raised to the x minus 2. How about that? So when we want to know our slope, we would be plugging in x equals 3. Well, we already know what we get when we plug in x equals 3. We get e. We did it right there. So the slope of the tangent line would be e. That makes the slope of our normal line, perpendicular, negative 1 over e. Cool. Remember, this is x1, y1. So now we just plug in. We have y minus y1 equals the m we found for the normal times x minus x1. And there you have it. There's no reason to go any further because it didn't say show that. Now, if it said show that, we might have distributed, and I believe we did that in the last unit, where I was told, well, show that the derivative of this exponential is something else than tangent line. But we weren't. We weren't instructed to do that, so I'm not going to do any more work, lest I make a mistake and get no points. Okay? Okay. Now for the last one. This last question is going to mimic, I believe, number 7 from the homework, the last one in the homework. It's not in the textbook as an example. I had to go online to find one, because believe it or not, this would have been really hard to come up with, but I found a good one. I like the way it works. We've been told to find the x value for when the normal to this curve at x equals 2 hits the curve again. You see, yesterday, when I made the notes, it was yesterday, for the last lesson, talking about tangent lines, we said, yeah, occasionally a tangent line will have to go through the curve somewhere else, not at the point of tangency, but somewhere else. Well, guess what? Normals can do it also. I mean, it could happen. So we've been instructed to figure out where the normal line that goes through this x value hits the curve again. All right, well, the very first thing we're going to have to do is we're going to have to figure out what our y value is, just like all the other examples. I have that x equals 2. So the y value would be 2 times 2 minus 4 over 2. Well, that's just 4 minus 2, which is 2. So coincidental again, but x comma y is 2 comma 2. Now to find our slope, I'm going to need my derivative, my gradient function. It'll be easier to find if I write this in exponential form. Well, if I write it with the negative exponents, that way I can just use my power rule. So let's rewrite y and say that it's 2x minus 4 times x to the negative 1. Bring it to the top, make the exponent negative. Now finding its derivative is very simple. They're two different objects, so we start here. Derivative of this linear is the coefficient, and minus 4, because it's just coming along for the ride. Now here's the thing. I'm going to bring this negative 1 down, and I'm going to multiply it to this negative 4, and it's going to create a positive 4. And then I'm going to subtract 1 from my exponent. And I'm going to clean it up since I do have to evaluate. There. We can now find our slope simply by plugging in x equals 2. This is the slope of the tangent. You always get the slope of the tangent by plugging in x into the derivative. It's going to give me 2 plus 4 over 2 squared. That's 2 plus 1, which is 3. But we're talking about the normal line. So the perpendicular slope, or slope of the normal, would be negative 1/3. Coolio. Let's find the equation of our normal line. Y minus y1 equals the perpendicular m times x minus x1. So what do we know? The directions say figure out where it meets the curve again. That means this line and this curve meet each other at least 2 times. You see, this curve says y equals. If I want to figure out where they hit each other in space, I need to be able to set them equal to each other. This one already has y by itself. So if I get y by itself for this one, then I can just set the two equations equal to each other and solve for x. We're going to do that by adding 2 to both sides. I'm not going to distribute this negative 1/3. Why, Mr. M? Because I don't want to mess with fractions. That's why. There. Now they both say y equals. See, that one says y equals. Can I get them both on screen? I can't. Well, anyway, this one says y equals and that one says y equals. Setting them equal to each other looks like this. Okay. Oh, you know, we don't want to have to mess with fractions. We just don't want to. So what I would like to do in one fell swoop is I would like to get rid of all of my fractions. Now, normally the way we get rid of them is by multiplying everything by the denominator. But I have 2 different denominators. So what I'm going to do is I'm going to multiply everything by both denominators. And you know what? I also don't want this negative sign here. That's just a me thing. It wouldn't have mattered. You could have got the same answer regardless. So I'm going to multiply everything by negative 3x. I'm doing that because this negative and this negative will now cancel. This 3 and this 1/3 will now cancel. And this x and over x will now cancel. And I will have no fractions when I distribute this negative 3x to all of the parts. You can't distribute it to the inside of the parentheses because those parentheses are being protected by this fraction right here. So no, it does not go to the negative 2 and the x. That's just not how math works, okay? Because these two things are being multiplied together. You're multiplying this negative 3x to the system that you have here. Alrighty, so negative 3x times negative 1/3 is just going to leave me x. Sorry. And when I multiply negative 3x times this positive 2, I'm going to get negative 6x. Negative 3x times 2x is going to give me negative 6x squared. And when I multiply these two negatives, they become a positive. The x and over x cancel. 3 times 4 is 12. Distributing the x gets me here. Obviously a quadratic. I need to get everything to one side. Since my x squareds are positive over here, I'm going to move these two objects to the left. Oh, and by the way, I'm also going to combine these two because they're like terms. So moving the 6x squared over here with this x squared gives me a 7x squared. Negative 2x, negative 6x gives me negative 8x. And then subtracting 12 from both sides gets me here. And guess what? This quadratic will factor. Your job is to figure out, I'm going to go ahead and model the Lizzie method in case you've forgotten how to do it. Your job is to figure out which two numbers will multiply to a times c, which here, 7 times negative 12 is negative 84. And they have to add to b, and b is negative 8. Ooh, got close to the edge of this paper. So the two numbers that multiply to negative 84 and add to negative 8 are 6 and negative 14. It might have taken you a little while to get there, but eventually you would have. So what you do is you put your two sets of parentheses, put an x in the front of both of them, and these two numbers get their symbols. This is a positive 6. This is a negative 14. But both numbers have to go over the a value of 7. Reduce your fractions, if you can. And we can now see our two solutions. One, when x equals 2, duh, because, you know, we were told that the normal line hits this curve at x equals 2. And the other one, which would be what we're actually looking for, because it says find the other x value, would be when x equals negative 6 over 7. And that is it for normals. And I believe the question in my notes right here is harder than number 7 in the textbook. So anyway, should you need any help before I schedule the big Zoom meeting for everybody that wants homework help, please just let me know. If I can help you through Remind, I will, and if that's not good enough, I'm more than happy to hop on Zoom, 1 person, 2 people, 16 of you. I don't care. I just want to help you all out. Anyway, I hope everything is going well for you in other classes, and I will be talking to you soon.